So today, let's continue our discussions on how LLMs are trained to handle tools. So I'll just do a quick recap of what we did last week, right? So that you guys are back to speed. So we talked about how the first paper on how tools were augmented along with LLMs, which was GSM 8K. And then we talked about a few different papers that sort of added tools during the fine-tuning process so that LLMs, in addition to responding back to users, could also have the ability to work with tools, right? And one of the common issues with all the proposed approaches back then was that they cannot generalize to tools that were unseen during train, right? And for every tool you have to add, or you have to let the LLM know, then you need to create a bunch of examples for them and then retrain the whole thing, right? So whereas TALM required a lot of human annotations, PAL required fewer annotations but could only work on Python related outputs or tools, right? And ToolFormer came in, which said that it can generalize, it can work with multiple different tasks, but at the same time, it cannot work with unseen tools. They require fewer annotations, so there was slight progression in how much effort is needed, but still this is considered to be significant effort, mainly because if you have to develop an agent and you have access to, let's say, 5 or 6 tools with you or APIs with you, then you would have to end up fine-tuning your model, right? Which is a very costly approach, because every agent requires fine-tuning and then they require hosting, and there's a lot of cost associated with it, right? So now in today's lecture, what we will see is how do we create fine-tuning data for LLM in such a way that it can generalize to tools that were unseen during train, right? Again, we will start by going through few important papers and then with slight progression on how each paper improved over the other, right? So before jumping into the details, let's first take a step back and see why do we need this to begin with, right? So let's take an example where, let's say that you are building a chatbot for IIT Delhi using LLMs, right? And your goal is that you have a lot of documents about IIT Delhi rules and all the policies that they have, and now if you have to build a chatbot over it, how would you build? Like, provide solutions based on whatever you've read in the class so far, right? So how would you build one? Yes, you can use retrieval augmented generation. So basically you split the documents into multiple chunks, index them, and when a new user query comes, search the index, get appropriate documents, and let the LLM answer, right? So you would use LLM during retrieval, and then you would use LLM during generation of the response, right? So now let's say that one common task that all students do is, when during the beginning of the semester they search for courses that are being floated this semester, and then they will register for some courses, and during the semester they might even drop courses, right? This is a very common task. And let's say that now now you've been asked to add this functionality into your chatbot, right? So how would you go about doing it?
So external.
Yes, absolutely, right? So there is a database where all the registration information would be available, right? And at this point in time, you guys use a web interface, which anyway would be connecting back into the database and updating things. And that web interface would have access to APIs that are being exposed by the database, right? So now if you have access to tools, right, or the APIs, then how would you augment your existing RAG bot into supporting this as well? So I'll give you a hint. In the previous class, we did synthesize some data for tools and teach the LLM, right? So that is one way in which you can do, right? So you can create an example for search, an API for, there would be an API for search, there would be an API for adding courses, an API for dropping courses. You have 3 tools with you. So you would synthesize examples and then you would add it as a part of the fine-tuning step. So Now, when you fine tune with this, maybe your model's ability to do RAG may drop, right? So then what would you do? You would have to add RAG examples to make sure that it doesn't drop there. Now, there may be complex reasoning questions that students may ask about policies where you have to relate 3-4 different policies and then arrive at the answer. Then you have to add data for that. So what would end up happening is that if you have to support new tools, you'll have to synthesize data for it. And during fine tuning, you lose out LLM's ability to do usual things. And then this becomes a very difficult loop to sort of figure out and then create a bot that is just a simple bot for IIT Delhi, which just supports 3 tools and then simple RAG, right? So then imagine like if you're doing enterprise level or a banking solution related tool callings, you have so many tools, so many APIs, so many rules about the bank in which things have to happen, like it becomes so complex, right? So the ideal strategy would be that out of the box, LLMs should support tools, right? If they give you GPT-4 should already have access to tools, and they do, right? So now what we're going to see is how is that they support the tools, and then how you end up creating data, which typically would be end up being used in the instruction fine-tuning phase, right? So that whenever it learns the other things, it also ends up learning how to use tools and any tool you provide during inference, right? So with this, let's go to how, and let's say that you have a model, let's say it could be Mistral or Claude or GPT-4, and when these models exist, there is always an application layer on top, right? So even when you use ChatGPT, it may not necessarily mean that you're directly interacting with LLM. There may be an agentic middleware in between that sits, right? Because when you ask for, let's say, calculation related questions, it does run Python script and then get you back results. When you ask current events related queries, it would search the web, get the results back, and then call the LLM, come back and give you the results. So there is always an application layer that sits, right? So typically the user interacts with the application layer. The application layer will have access to some tools as well, or mechanism to call tools and get back responses, and then there would be an LLM which would be which the application layer would have access to, right? So let's take the same example of adding, searching, or dropping courses and see how it would work, right? So let's say that you go to the application, and as a user, you say that this is the IIT Delhi, assume that this is the IIT Delhi application, and say that I want to register for AIL 861, right? So what would happen is that this application layer would have access to the 3 tools that you have, right? And all you have done is that you've registered those 3 tools. You have not given examples, you have not given anything else, you're just registering the 3 tools. And here it says the tools available are add course, drop course, and search course, right? And maybe some more details associated with what are the input arguments, what are the required attributes, what are the optional ones. For optional, what is the default value, right? And it may also say like what would the output structure look like the JSON response that comes back, right? So each tool will have some description associated with it. For brevity, I've just included the name of the tools. And along with that, the application layer would also say like, look, these are the tools available, and this is what the user wants. Now tell me, now the model has to make a decision about whether it requires to use any tools or not, and if required, what tool to use and how to use it, right? This is what the LLM should decide. If it was a RAG query, let's say that are there any, if I drop a course, what are the consequences, right? If your question was that, it may not choose the drop course tool there, right? It may just say that I don't want to use any tools, rather I want to search or use RAG, right? Something like that. But in this case, it should decide that it has to call appropriate function, which is add course, right? So what the LLM would come back is that when the prompt goes in, it went with the user input and the list of tools. And what the LLM would give back is some token that says, at this point in time, I want you to execute a tool, right? And says the tool is add course. So let's say that when you logged into the portal, it already knew your student ID. So student ID and the course ID, it took it from the query the user gave, which is AIL 861, right? And then it sends back to the application layer, right? Now the applications layer responsibility is to execute the API and let's say that the response here from the API execution comes back with student ID this, course ID this, and current status is registered. So it was able to register. Maybe if it was a failure, then it would be a failure. And in this case, let's say that it got registered. So now, once the response comes back, then the application layer again will send in call to the LLM. And at this point in time, what it would do is, it will say that what are the tools available. It would say what the user initially said. It would say what the assistant said in the previous call, which is make a tool call with these parameters and to this function. It would also contain the tool response, right? And at this point in time, the LLM should figure out if it has to call more tools, or if it has to do RAG, or if it just can generate the response back to the user, right? So at this point in time, it looks like it has all the information necessary, and it has executed what was requested from it, and then it can go back to the user and just say you've been registered for course AIL 861, right? So this is going to be what typical function use of unseen functions would look like, right? All you need to do is register what all tools are available in a certain format, and the model should be in a position to make all the decisions and then make it work for you, right? So there is no fine tuning required. You just have to specify what tools are available, right? So now in the remainder of the class, we'll see how we would end up generating training data of this type so that you can use it during instruction fine tuning phase, right? So typically a function definition would look like something like this. It would be a JSON object which would have the name of the function, the description of the function. It would have all the parameters it supports. Here it supports properties like transaction ID, which is a string. If it has default values, it would have default value. And then here it says at this point in time, there's only one parameter, but if there are multiple parameters, it would say the required parameters are what are the subset of the parameters that you have. And of course, you can all, in many cases, a well-defined function description would also have what is the output type, right? Output type will also be a complex JSON object, and it would say what all information are available in the response that comes back, right? And there is an application layer that sits in between, right? So it is not always necessary that you have to create a REST API and then call and get back, right? If you use an application, if you use LangGraph to build your application, then it also supports Python functions. You can create Python functions of your own and then define some tool annotations which will expose that as an API, right? So when you design it, so you should not always assume when I say tools, it's just APIs. It could also mean Python programs or any other language programs, right? So now, yeah, so the overall process, like just to repeat, right? When you design the application, you have to register all the tools that you have to the application layer. And then when the user enters a query, here it says, what's the status of my payment? My transaction ID is T1001. The model identifies whether to call the function. If it has to call a function, what function to call and what arguments to provide. That's step 2. And then the agent or the application layer will execute the function and provide the results back. And again, it goes back to the LLM until the LLM generates a natural language response. If it again generates a tool call, then again it would go back to the application layer. It will execute it, give back the results. So the iteration keeps continuing until the LLM says a natural language response, which is not a tool call, right? So this is how it's going to look like. So now, how do we teach this to the LLM, right? So obviously, we'll have to construct examples using something similar to what we saw in the example, in the introduction example, right? So if your input is the tools are available, the user says this, then you have to output something like this, right? And similarly, if the tools available are here, the user says this, the assistant says this, tool response is this, then what should you respond back, right? So you need to gather a lot of examples of this type and then use this to during the instruction fine-tuning phase, right? So I'll talk through some papers which sort of generate data of this type, right? The first paper is going to be about the paper that introduced this notion of how do we generalize well to unseen tools. Right? This was a paper that sort of hinted towards the direction, but in parallel, OpenAI was also working towards tool calling. So once the first Gorilla paper came out, OpenAI, in a matter of month or so, they also exposed how do we use external tools with ChatGPT or GPT 3.5 at that point in time, right? So Gorilla was the first paper that created a data set with which you can evaluate tool calling ability of LLMs with external APIs, right? And then they showed like how do we design the training examples so that you can generalize to examples that were unseen during training, right? So as a part of this effort, they collected or they synthesized a data set called APIBench, right? And it sort of used all the model cards from a lot of these model hubs like Hugging Face Model Hub, Torch Hub, or TensorFlow Hub, and then they created the data set. So I'll go into the details of how this data set was created. And they fine-tune Llama 7 billion model with the APIBench dataset they synthesized, and they create something called the Gorilla model, right? So this is a tool calling model. So the reason why they fine-tune is that they fine-tune to show that it will generalize to unseen examples, unseen tools as well. But fine-tuning is the easy way to demonstrate that it works, right? So ideally, you should have used these examples during instruction fine-tuning phase so that the model learns tool calling in addition to other tasks, right? So any questions so far? All right. Okay, so the first step was data curation. So as you see that they have three different sources of model, right? Three different sources for getting the model cards. So what they did was they collected a total of 1,645 model cards from different sources, and they converted them into a standard JSON format, all three, right? So this is sort of synonymous to how tool definition, the example of a tool definition I showed. They were not there yet, but this was how they started with, right? So a common format to represent tools. And so they have a lot of keys, which may not be very generic, which may be specific to model cards. Some of them are generic, like API name or the description. These are generic, but many of the other things like performance of the model, or what framework it uses, or what domain, like domain framework, these are very specific to model cards. But their idea was that we need to have a single way of representing all the tools so that model can sort of understand and then use them accordingly, right? So that was the first step they did. And in the second step, what they did was, now that you have definitions of each model, now how do you construct input-output pairs with which you can fine-tune the model, right? Like I showed you before. So for that, they use something called self-instruct. So I'm not sure if this has been already covered during the instruction fine-tuning phase, but they use the same technique here to generate 16,450 examples, which is basically 10 examples per API call or per model that they had filtered, right? So an example of the input-output pair was something like this. If you were talking about SSD MobileNet version 2, then it sort of says that this is the way in which you access it. And then with that, you can create a query like, our customer is a zoo and we want help to help them detect movement of different animals. Write a Python program in 1 or 2 lines to call the API in TensorFlow Hub, right? So what they did was they provided a bunch of seed examples, right? And they sample from the seed examples and give one of these APIs. And then for that API, the model would, an LLM would end up generating the user utterance, right? So because they already have the API call available with them, they have to generate examples. They need to create the user utterances, and they use self-instruct along with some seeding context examples to sort of create 16,000 pairs of input-output, right? Now, once you have those examples, you can train the LLM. So in their case, they trained Llama, I think, and then they got Gorilla 7 billion model. Now let's see what happens during inference, right? So if you only used these examples to train, user and then assistant is the output. So which means like you are in some sense forcing the model to memorize all the tools, right? That's what they have done here. There is 1600 APIs, and they have made the model memorize all the 1600 APIs. If you use user and assistant as input and output, right? So during inference, what would you do if somebody says, I want to see some cats dancing in celebrations, right? Which means they want to generate an image of cats dancing. Then you would directly pass that input to the Gorilla model, and the model would predict what API it should call with what parameters, which it which is in his memory, right? And then it would end up generating the final image, right, when you execute this. Now the issue with this approach is that, of course, it cannot adapt to unseen APIs, right? If you add more APIs, it cannot do it, because again you'll have to retrain from scratch. And many a times what happens is, like, people end up changing the model weights and they update it, and then they say that the API name is the same, but the model you have to call has now changed to the latest version. Now this is a very, very frequent phenomena, right? In 16,000, if you use 16,000 different, 1600 different models, then of course every day one model is going to change, right? At least. So this was not a very viable solution, because it means every day you'll have to retrain, right? So what they suggested is, like, make a small tweak into how you train the model, right? So this is a paper that said that in addition to the user utterance, also train with the API reference as input, right? So which is exactly what the JSON they had constructed while converting all of the model cards into a standard format, right? So if you have a standard format of representing tools, then add the tool format in the input along with the user query, right? So they started with one, but like you can generalize it to, you can also show like 3 or 4 different tools. The model can end up selecting which tool it wants and then use it, right? So this was a paper that first talked about this, that you have to use APIs as input as well, API definitions as inputs, so that the model learns to adapt to new APIs unseen during train. And of course, when you were providing this as input, then of course the model weights change, you can point to the new model weights right in this definition, right? So it's as simple as that. You don't have to retrain, you just have to change the tool definition, which is a much easier process. So now what happens during inference, right? So when they created, when I said that they converted everything to JSON, you could as well take all those JSONs and index them in a retriever, right, in an index. And once you index them, then when a new user utterance comes, then the first thing you would do is go search through the API database and figure out what are all the relevant tools that you can use, right? So that would be the first step. And let's say the retriever gave you one tool for now, right? And then you would feed the Gorilla model the tool, which will also go as input, and the user utterance, which will also go as input. And the model will then predict the tool to be called, and then you could execute it, right? So as I said before, this will lead to better generalization, because now in your API database, you can also add new tools. In this specific scenario, you can add more models, right, that were not seen during train. And of course, you can always change the tool definition, tool description, and all the parameters in the tools even during runtime without having to retrain the system, right? So this was a major change in how people perceive LLMs should interact with tools, right? So these guys also introduced a new evaluation metric called AST match, which basically is how typically code modules are matched, right? Abstract syntax tree. Like when you have 2 Python codes, doing a strict string match to check whether both are the same or not is a very bad idea, right? Because there are multiple ways of writing the same code, and just because the surface forms don't match doesn't mean that the code generated is bad, right? So what people typically do is they go one level of abstraction higher, and then they form something called like how variables are linked, what operator is used, right? They create a tree structure of what the code does, and they create a slight abstraction of the tree structure so that the variable names don't have to be the same, right? And things like that. And then they match that to understand how good the 2 codes are or how close these codes are, right? So they adapted that as an evaluation metric, which basically says that, look, even if the arguments are not in the right order or things like that, those all will be taken care, right? And you don't necessarily have to define a default value. If the value is default, even if you explicitly say it is fine, if you don't say it also is fine, because eventually you end up getting the same thing, right? So this abstract syntax tree match is not exactly strict string match, but slightly it covers a lot of different scenarios, which means like 2 programs or 2 function calls are synonymous, right? And in addition to reporting AST accuracy, this paper also reported 2 metrics, which was a big problem back then, which is even when you provide certain tools in your prompt, the model will end up giving you a tool that was not there. It just makes up tool names, right? Or it would make up arguments in the functions, right? So these hallucinations are really bad. So they want to say how different to compute hallucination. They would check the output which are wrong, and then they would see that whether the name or the arguments were hallucinated. So that indicates how much hallucination. So lower the hallucination, the better, right? 0 is the ideal, but lower the better. And similarly, apart from that, you might have other errors like you picked a tool, but that was not the right tool. Like you didn't hallucinate the tool, but the tool was incorrect, and or you incorrectly filled up some arguments. Let's say if it was an enum and it allows only 4 values, maybe you gave some value that was not accepted, or the user said something to generate cats, and then in your function call you did not say cats, you say dogs or something, right? So you call the API right, but somehow something didn't add up right? But that's not hallucination. So they have hallucination rate, they have error rate, which is not hallucination, and then they also report abstract syntax tree accuracy. So now let's see how different models perform in the 0-shot setting, which is no retriever setting, right? You let the model memorize everything, right? And then you try to do. Now, in case of, so of course, like Gorilla is the only model that has been fine-tuned for this task, so it has to do better, right? So there's no big insight in that. And of course, other models might have seen a lot of information on the web, so they might have tried their best, but they cannot do much, right? So what is interesting is what happens when you provide them with access to tools, right, in the prompt. So when you provide them with access to tools in the prompt, you see like GPT 3.5, GPT 4, Claude, their numbers jumped considerably now. So just when you provide tools in the prompt, they are able to make use of it and then provide reasonable accuracy. But some things are important, like in Llama, it looks like most of the issues comes from severe hallucinations, right? So in other cases, things are similar. But here you see, like in most cases, Gorilla is a small model, but it's doing as good as most of the big models, right? That was a summary here. And then they did one more experiment where rather than providing a retriever, they provided the correct reference library. So in some sense, you're hinting the model that this is the only tool available to you, and that's the right tool. So you just have to do a good job in filling the arguments and then calling them appropriately, right? So when they do that, again, they also show that the numbers are considerably higher compared to what you would reach with GPT index, right? So which, like, there is a jump here from 47, which is the best, to 91, right? Like, there's a severe jump. Similarly, there's a jump from 65 to 95. So what this, and Gorilla is very close to what, in most cases, Gorilla is the best. In cases it's not, it's very close to the best, right? So what they say, so this paper concluded saying that if you are to work for unseen tools or things like that, then you go with this approach of giving the tool description in the prompt. And they also said that in the current state of things, you have to use a retriever, and these retrievers are really bad, right? So with a good retriever, with an ideal retriever, you could achieve 90% accuracy, but with whatever state-of-the-art retrievers was there back then, which are not very specific to tool calling retrievals, but rather more like document retrieval for RAG. So those were not good retrievers. So these are the main 2 takeaways from the paper. And these guys, the people who wrote this paper also came up with something called Berkeley Function Calling Leaderboard. Of course, the paper was from University of UCB, and so they called it Berkeley Function Calling Leaderboard. And after they introduced, now they have like V4 as well. So they gradually increase the complexity of the test benchmark, and then now they have V4. This is sort of the standard de facto tool calling benchmark that exists out there. So if you want to know how each different models perform on tool calling, it's good for you to go to the BFCL leaderboard and check where that model stands, right? So as of now, I think Claude is the best, and GLM is slightly above that as well, right? And of course, there are multiple different things for singleton, for multi-turn, and then there is something called V4 format sensitivity, V4 agentic solutions, and these are like an average of multiple things. And generally, within each, even within multi-turn, there are multiple subcategories as well. So it's a very exhaustive evaluation benchmark, and this is a good representation of how good these LLMs are for function calling. Yeah, so to summarize, APIBench was one of the first papers that talked about retrievers in tool calling. Their diversity of APIs is very low. They just work with model cards. We don't know whether it will generalize to any tool that exists out there. And of course, these are very simple dialogue, singleton. The user says everything they want very clearly in the first utterance, which is never the case. But very rarely, people who exactly know what they want and they know what tools exist can do this, right? But typically, when you go, you may forget to say something which may be obvious for experts but not for novice, right? So this is a very very restrictive scenario, but it's a good progress in that setup. So the next paper we are going to see is called ToolAlpaca. So here the main difference compared to the previous approach is that they use 4 real world inspired tools, right? And again, like the synthesis is similar. I'll talk about some details, and then they end up again fine-tuning an LLM called Vicuna, and then they call the model ToolAlpaca. Right? They have not named their dataset here. So basically, what they did was they went to this GitHub repo called Public APIs, which is basically people like us who would document all the APIs that exist out there that are free to use. Right? There are a lot of public APIs that are available free to use, but this is one place where the community has pooled in, and then they update the list of APIs available. So they use that to get a list of like broad apps and what they do, right? And they also list all the APIs within that app as well, right? For example, there may be one for Dropbox, there may be one for getting public holidays, and which may have like different things like search holidays or get by country. Multiple APIs might be inside it, but this is sort of the app and they give. So they only took the name of the app and the introduction of the app from this public APIs, and they have 1400 of them, right? And with that, they prompted an LLM. Like first, the LLM, given the title and the introduction, would generate a description based on few short examples like self-instruct, and then given the title, introduction, description, it will create some function documentation. Here it lists all the functions. Here it provides some more details about what each function does. And then for each of the function, it would end up generating the entire open API spec. The open API spec is one of the examples that I showed you in the first, when I was discussing the motivation, right? It has all the required parameters, all the parameters, descriptions, default values. That JSON is called the open API spec. So they ended up generating an open API spec for each of the function that they have, right? So this is why it's called inspired. This is why they say it's real world inspired. They did not actually use the same APIs, but they took just the app name and the introduction from there, but they ended up generating their own stuff, right? Now from this, they have to generate dialogues, right? So they have 1400 tools. Now with those tools, they have to end up generating dialogues. And the way they generated dialogue is that they had 3 different prompts, right? One was a user prompt, one was a prompt for the user, which would end up generating user utterances, right? Which, like if you say you give this API and these 3 tools, it would come up with, I'm planning a trip to Japan next year and I wanted to avoid any major holidays. So can you tell me the list of holidays in Japan next year, right? So given this tool, it has created a user utterance. And then there is an agent bot or an assistant bot. The assistant bot will say what it wants to do. It could say that I want to chat with the user, or it could say that I want to call this method called get holidays. And then it would also give all the arguments associated with it. In this case, it says that could you please specify the year you are planning your trip for. And in case of get holidays, it may follow the description here for get holidays and then give date and type and country and year, right? Country and year, which is what is described here, right? And then there is also there's a prompt for tool execution, which is if you give the open API specs for get holidays, it would have the response object as well, right? So based on this query, it would synthesize the response following the response object format, right? So these different prompts will act in tandem, and then they will generate the dialogue, right? So the way they coordinate between is basically using rules, right? If the first utterance, it has to be the user, right? If it is chat with, then the user has to hand over the control to the assistant agent for sure, right? Whenever after user, it has to go to the assistant, and if the assistant says chat with user, then the control has to go to the user agent, right? And if then after user agent, again the control has to come to assistant agent. When the assistant agent says any API that is available, then the control has to go to the tool executor agent, right? So it is a very deterministic flow, but the only difference is that they use different prompts for generating different parts. The reason why they do this is because if you give all the prompts together as a single monolithic prompt, then it typically doesn't follow all the instructions very clearly, and even a single point of failure would result in the dialog becoming incorrect, right? So typically it's a good idea to break your prompts when you do synthetic data generation so that you can avoid that failure, right? So they use three different so they used the way they evaluate the different models are by calling GPT as or LLM as a judge, right? They have different dimensions. One is called the procedure, which says whether you call the right tool, whether you use the right arguments and things like that, and response, which says whether the final response that you generated is correct or not, and then overall includes both procedure and response. And they also did a human annotation to see whether these LLM as a judge correlate with humans. So as expected, ToolAlpaca, the model, the Vicuna model trained using ToolAlpaca was doing like as good as GPT 3.5. Right? And here the only difference compared to the previous approach is that the tools are a lot more exhaustive and real world, right? And if you see here, these tools, simulated tools, are not the same as the tools that was used during training, right? The training was done with 400. These are not the 400. And similarly, they also took some real world APIs which are not simulated, right? The entire description, open API specs, everything was real world. And then they use that also to show that if you train on whatever we synthesized, it would also work well for real world. And these were very close to what you would achieve using GPT, right? Like at this point in time, it's 10 points. But if you see other small models which are not trained for function calling, were really bad. But once you train it with this approach, they're very close. And in this case, simulated tools, it's even more closer than the other one. So the ToolAlpaca showed better diversity. It also showed multi-turn dialogues, but the only common part between the both is still they use only single tool, right? Only one tool is where the entire conversation is grounded on. All right, so let's go to the next approach called ToolLLM. So these guys use a lot of names. Their dataset is called ToolBench and their model is called ToolLama. And it's the same approach. The only difference here is that rather than using simulated APIs, they ended up crawling real APIs from a marketplace called API Hub, and then they used that to synthesize the data. Now that comes with a lot of issues because these are real world executable APIs. Like these, if you pass arguments, they can actually execute and give you back results. You don't have to synthesize any tool responses, right? And so they totally gathered 53,000 APIs, but from there they ended up only using 16,000 APIs because others were outdated. You are not able to execute. They were not able to execute them, so they filtered and they took only 16,000 that were functional. And what they wanted to do was they wanted to focus on generating dialogues that requires multiple tools, right? So rather than sampling only one tool, they sort of Rapid API sort of organizes APIs in hierarchical groups. Like these APIs can be are from a similar application, and these applications are from similar domain. So they sort of group them together. So based on the groups, they sample tools that are cohesive, and then they gave n tools to an LLM and ask it to generate user utterances, right? So one example here is like they had tools like entrepreneur mindset collection, random words, the digital news feeder API, chemical elements. So, and then they gave this to the instruction generation prompt, and it would generate query like, for my best friend's surprise birthday party, I require inspiration for party games and decorations. Kindly suggest some random words that can serve as theme for the party. Furthermore, I'm interested in gathering news articles about the latest party trends to ensure modern celebration, right? So here, this is what the LLM would generate as a user query for this subset of tools, and it would also say it didn't use all the tools, but what tools it ended up using for generating this particular instruction, right? So this is how it ended up generating instructions. And then now the main part is once you have the first user instruction, you have to generate the dialogue, right? So how do you end up a dialogue that looks realistic, right? And for that, when they prompted LLM to generate dialogues like what the previous approach did, which is like do a multi-agent approach where first user generates a user prompt and then agent generates an agent prompt, and then tool executor. You can replace a tool executor with a real executor, but if you go by that approach, they were not able to get good results. And the main reason for it is that if the tool calls were not made right, then the tools will return errors or some failure, and then it would get stuck in the loop and then keep doing the same thing again and again. So you would not get like realistic looking dialogues with which you can actually train, right? So let's see how they changed it, right? So let's take this example in the right. So I want to give my friend a birthday surprise. I know her favorite actress is Hailey. Help me, please. Now, the first API that is called is to get more details about Hailey, so that it can think about what it can like suggest, right? So now when that particular tool call is made, get extra character details, and the name is Hailey Steinfeld, then the Rapid API can either give you the exact details, right? Or it can say server error or any other error. Maybe you didn't put the arguments right, so it may give a different error. Maybe it ended up like saying that additional required parameter was not given, things like that, right? And then based on whether the API execution was successful or failure, you could finish with a good final answer, or you could end up with giving up, saying that I don't know what to do, I tried. Sometimes it may go in loop as well. Again, the model would say that let me re-predict the API name and API arguments, and then it never would come out of the loop. Like after 30 tries, it would still be stuck in the loop. So what this paper says is that if you go by the usual approach, like one after the other, then at some point in time you will end up facing errors, and it may go in circles, and finally you end up generating a failed trajectory. And this failed trajectory is typically not a good thing to learn, right? So what they said was, let's go do some sort of a depth first search, which is, if I know this failed, then I go back to the place where we didn't fail, and try something slightly different, right? And maybe that also failed. So then they may come, when they keep doing depth first search, finally you will hit a point where you would be able to respond back to the user, right? And that path is what will be taken as a example, right? Others would be ignored, right? And then of course that becomes the ToolBench dataset, and if you do SFT of ToolBench on Llama, they end up getting the tool Llama thingy, right? And in addition to that, what they also did is, like in the previous approach we saw that retriever is a crucial component, and they clearly said that these retrievers are general purpose retrievers are really bad. So what they did was they ended up training their own retriever. The advantage they have here is that, if you remember, they have this setup, right? This was generated as a part of their synthetic data generation. So they know for this query what are the right APIs to call, right? So they could use this as training. They could use this to synthesize the training examples for retriever, and they ended up training a retriever as well, right? From the instruction generation phase, they could use the user instruction, the relevant APIs to train an API retriever. Yeah, and of course during inference, once the user instruction is given, you would hit the retriever, get relevant APIs, and then you will keep interacting with tools as and when the LLM tells you to. And then once all the tools are, and the model gives you a final response, then give it back to the user, and then they will evaluate how good that output was. Again, they use similar metrics as the previous paper, which is hallucination rate and abstract syntax tree accuracy. And here also they say that with retrievers, the abstract syntax tree scores are much lower, right? But when you use an Oracle retriever, then the numbers are much better. So still the retriever is not that great. But what I suspect, the reason why I suspect why they used their own retriever rather than doing their performance using out-of-the-box retrievers, is because I think their model was not able to achieve as good accuracy as Gorilla with regular retrievers. So they ended up using their own retriever for their approach. It feels slightly manipulative, but I think that was the reason why they used API retriever and not BM25 in that setup. Right. So now ToolBench, the main advantage was that they identified something called Rapid API Hub, which has real-world specs, and their dialogues are grounded on multiple tools, right? Which is more realistic than a single case. Now let's go to the final paper that we would discuss called APIGen. So this was a paper by Salesforce, and they generated around 60K examples again from Rapid API as the grounding tools, but they ended up generating only single turn tool calls, right? They did not use multi-turn, and their main focus was BFCL, right? BFCL is the leaderboard that I showed you in the beginning that Gorilla people did, right? So when this paper came out, BFCL V1 was out, and their goal was like, how do we get top numbers in BFCL, right? So this paper, although it has some new things, but the target was to get better numbers on BFCL, and so some of the design choices would be geared towards that, right? So basically, this is an example of how the dataset would look like. The input would be, I want to know the weather in Palo Alto, and the available functions would be like check stock price, get weather, fetch news, and things like that. And then the model should predict get weather, Palo Alto, and today, right? This is how the function call would look like. They didn't focus on generating the final user utterance, right? Or they did not even worry about making this executable and getting back the results, right? Because BFCL did not have the evaluation, did not have evaluating the response. Their evaluation only had evaluating the function calls being made. So they generated just the data that given the user query and a bunch of tools, they would only generate the tool call, right? That's what their data was focused on. So yeah, so for first they have a bunch of APIs. They took the same APIs as what the ToolBench did, and then got all the Rapid APIs. But what they figured out was that out of the 16,000 APIs that ToolBench made available, most of the APIs, maybe the descriptions was generic, right? And they were having high latency in the sense that you query them and you get back response after 3 or 4 minutes. So they had multiple issues that was not very that made them very flaky, right? So they removed most of the things and they only kept 3,000 good execution ones. And in cases where they felt descriptions were not very clear, they enriched that metadata using GPT-4, right? So if the description, if the tool was booking tickets and the description was also booking tickets, booking underscore tickets and booking tickets, then they would make an LLM elaborate it a little bit more based on the required parameters and the response parameters and things like that. Even parameter descriptions were enriched and things like that. And then they also have some seed user question and function output pairs, right? So they use self-instruct again. They sample some APIs. They would sample some seed dataset. Like the sample APIs would be what you will want to generate the question on, and the seed examples will be the few short examples, and then they would end up generating the question answer pairs. But here the one main difference or the contribution was that they, after you sample them, all the existing techniques would just directly generate, right? But here they introduced a lot of diversity. Okay, let's see what type of diversity they introduced, right? So of course, simple things are question verbosity. Sometimes the user may be very crisp and clear in what they want, or sometimes they give background story of what they are doing and then indirectly say what they want and figure out. Like for example, if I have to, some question, is it going to rain in Palo Alto today, right? Or you can say like, should I carry an umbrella? Like, so, or say that I have an interview today, blah, 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 give the whole story and then say that I don't want my dress to get wet. Should I carry an umbrella? Like you can have different types of questions, and sometimes user will misspell certain things. So the reason why they had all these setup is because BFCL had examples like this, right? So since they want to do good there, they had these different types of prompts, and similarly, BFCL also had 4 different subcategories for single turn dialogues, right? Single tool indicates that the user says something, you have to use one call, one tool, and then you should get back the results, right? Multiple is the same tool call, but say you want to call it twice with different arguments. So for example, the single example would be what is the weather in Delhi, right? The multiple example would be like I'm traveling from Delhi to Bangalore. What is the weather in both places? So then it has to make 2 different tool calls with the same tool but different arguments. Parallel is you may have multiple different APIs that almost achieve the same thing, but there are small nuances in where they are different, and the model has to figure out from that, right? This is slightly harder than the usual single. Single, you may have very different APIs. It may be easy for you to narrow down and pick what you want. Parallel might be slightly different, and parallel multiple is a combination of both, right? So randomly you would pick a prompt based on all these different diverse set of prompts, and then you would generate QA pairs, right? So once they generate QA pairs, the good part they did was the APIs were already standardized, right? They were already in the open API format, so they were all JSON. Function calls are also always JSON, right? The answer is a function call for them, so it's always in JSON. And even when they generated outputs, which is like the answer type here, so they also have a standard sort of they represented in a standard way. The reason for that is because they wanted to filter queries that did not conform to a format, in the sense that you want the answer to have these fields, and if the model did not generate some of these fields, then it means it has made some mistake somewhere, right? So the format checker will help you simply look at the keys and values, and sometimes if the API specification says a key and then in the argument of the generated answer you have a different key, then those don't match. So they use simple rules to remove examples that were bad using the format checker. So they removed using format checker. Second was they also have another verification step where they would actually run the function call on the Rapid API execution, and if the execution fails, then they would ignore that example, because the execution can fail even when the arguments are not given right or it doesn't make sense and things like that, right? And finally, semantic checker, which is sometimes the execution may run, but still you might have given some weird, maybe a misspelled word was picked up rather than the right word, right? So output may not give any results, and because of that you would say something that does not make sense, right? So semantic checker would say that, okay, I will not look at tools, I will not look at tool output, I will just look at input and output, and then see whether the output looks something that makes sense for the input at hand, right? So with all these, one of the good thing they did was they showed, like, if you use different types of models, where all these models would fail, right? And they said that if you use a very big model like 236 billion model, then your pass rate was very high of all the verification step you have. If you have Mixtral 8 cross 7 billion, its pass rate is similar to the 33 billion DeepSeek coder, and 8 cross 22 was 65, right? So they sort of gave some. Until then, nobody talked about these things. Everybody were generating data with GPT OpenAI models, and those quality were really good. Once they started moving towards non-proprietary models, then this was a paper that showed, like, what is the model that you should probably be using, and how much how good they are. And of course, all this verified data doesn't mean they are good, right? It means that they've passed this multi-stage verification. There may be issues here as well, right? But this means that these are all bad for sure. This doesn't mean that all these in the verified data are good. And with this, so this was a screenshot that was taken when the paper was released, right? And then at that point in time, this model's overall accuracy was very close to what GPT-4 could do at that point in time. And this was Mixtral 8 cross 22 billion model fine-tuned with their data, right? So yeah, so basically, to summarize, Gorilla introduced the notion of having the tool description in the prompt, and ToolAlpaca started to explore with slightly more diverse data. ToolBench started to work with real-world APIs and multi-agent simulation framework. And then XLAM came up and said that you can tweak the knobs on how to generate, so that you generate a lot more diverse data than simply following what GPT or other models would assume, right? So diversity was the main focus there. But again, the issue here was that still it was grounded on a single tool, right? And it did not have multi-turn. So during the time frame when this type of data model was getting generated, in our team, we were working towards data that has permissible license, right? Because in all the previous papers, GPT-4 is used at some point in time or the other, right? In XLAM or the APIGen, they used it for metadata enrichment of the APIs. In other cases, they generated dialogues using GPT-4, and they did not have permissible license. Secondly, Rapid API specifications don't have permissible license, right? You can't use that to fine-tune your model and then use it for making money or for general purpose. You have to pay royalty to them. or you cannot use them directly if you want to use it for any purposes. Only for academic research it is allowed, right? So our team was working on mainly openness, which is like how can we create data using models that are Apache 2 and using APIs that are open source, which have permissible Apache 2 license or MIT license, and then work with them. So that was a main goal for our team. And of course, we wanted it to be generalizable in the sense that when we used most of these data sets, fine-tuned the model, and then work with enterprise or any other APIs, they don't generalize very well. Right? There is some bias in those APIs, and so they were not working well. And we showed that if you use multiple evaluation benchmarks, then whatever you trained on, it worked well there, but in other benchmarks it's slightly degraded by a good margin, right? So we ended up pooling a lot of data from different sources and then created a sort of training set and a benchmark which helps generalize. And third, during that time, that was a time where people started to build agents, right? So until this point in time, people's belief was that you give the tools, the model would be able to figure out everything that's needed, right? But soon they realized, like, just by giving the set of tools and the descriptions, model will not be able to stitch them together to answer, right? Because typically business process or any process involves would require a sequence of steps, and unless you know what those sequence of steps are, it will be very hard for you to stitch them together. Nobody is going to ask, like, I want the weather for Bangalore and Chennai, right? In banking, you would rather say that I want to open an account. Now you don't know what all procedures are there to open an account, right? So similarly, if you say open an account to LLM, there is not going to be a single API that says open an account with all the necessary parameters, right? Maybe there's a KYC phase, that output, once you get the key from that KYC phase, you need to do something else. Then you need to manager approval to create what type of account you want based on things. So there may be a certain procedure and policy on how to join things together. So people were not able to build usable agentic solutions with what LLMs were allowed there, right? So what they wanted was to break them into smaller tasks, right? Sometimes the procedure is listed and you as an application developer know what the process is. So you know what API to call. You just want slot filling, which is you just want the arguments to be filled, right? In some cases, when the user comes with a query, you just want to figure out what the tool has to be called, and once you select what the tool is, then you have other procedures to get the variables for the tools and fill them up. So while function calling is a task that has multiple subtasks like function, tool name detection, slot filling, validation, and what sequence of tools have to be called, things like that. So we broke the task into granular tasks, and then we taught LLM all the tasks along with function calling as well, right? So this was what we were doing at that point in time. And when we released this data and the model, we were the top Apache 2 licensed model with data on the BFCL leaderboard back at that point in time, right? So this is a summary of what we discussed today. Going forward, I will talk about slightly more about what is happening now. So this is until 2003 end, right? So in 2024 and 2025, most work has been focused on how do we generate multi-turn dialogues that are stitched with multiple tools that are more closer to realistic use of agents, right? That's what I'll be covering in the next class. And then I think there is a break of 3 classes. And after that, we will see if we put the models that are trained like this and want to build a realistic agent, what all obstacles you will face and how do you build a good solution with it, right? All right, thank you.